Good morning, grade 12s, and welcome back. And especially to our new friends, welcome. Hudisa Technical School, is that correct? Yeah. Welcome. Okay, so those of you who don't know me, I'm Mrs. Karen Venter, and I will be doing the physical sciences component. So a special welcome to everybody at home as well. We have a new set of notes today, so please ensure that you have the new notes with you. And then also remember, the first two lessons on work, energy, and power is already on the website. So if you haven't had a look at those yet, please do so. So let's just quickly recap. In the first lesson, we had an introduction to work, energy, and power. The different terms we used, the principles, etc. And then in lesson 2, we had a look at application and also how momentum and impulse is combined with work, energy, and power. Okay, so today we're going to gear up a little bit. We're going to look at more application of work, energy, and power. And today is the last lesson on work, energy, and power. So what I'm going to show you today especially is how you usually have at least 2 options to do work, energy, and power calculations. And this is where you need to decide as an individual which procedure or which application you feel most comfortable with. Whenever you decide on a formula to use, though, it is important that you know exactly what you need when you apply that formula. Okay, because there is a difference. So just to recap on our formula, you are now familiar with work done, net, is equal to the change in kinetic energy. And this is also the work energy theorem. So if you do have your first set of notes with you, quickly have a look at the table where they specifically give you the different principles. If you don't, we'll sort you out later. It's also on the website. Just quickly, the work energy theorem, you know, is the total work done on an object is equal to the change in the object's kinetic energy. And there you have the formula, change in kinetic energy. Then we also have work done is by a force. It's the force times the displacement, cos theta. Now you know cos theta, we usually work with either cos 0 or cos 180 degrees. And then the new one we're going to apply today is work done by a non-conservative force or forces. And this is where you have some decision making to do whenever you get to the assessment. Because first of all, and I want you, if you do have your notes with you, or you've got a paper to write on, make this note. The only conservative force that we work with, conservative, what is a conservative force? A force for which the work done in moving an object between 2 points is independent of the path taken. So the only conservative force, it's on the notes. Okay, we'll sort it out later. It says there, conservative force, and I want you to make the note. Conservative force that we work with is the work done by a gravitational force. In other words, if I look at this formula, non-conservative, work done by a non-conservative force, this means I need to exclude the work done by the gravitational force. This includes gravitational force and its components. So when I use this formula, I cannot include the gravitational force. Okay, and this is very important. So today we're going to look at application, especially between the work done by a net force is equal to change in kinetic energy, but also non-conservative is equal to the change in kinetic energy plus the change in potential energy. And to recap, the formula for potential energy is mass times gravitational acceleration times the height. Kinetic energy is half mass v squared. Okay, just to recap, so keep that in mind. So the first question we're going to have a look at is question 14. on your notes. So those of you at home, the notes on the website, the second set of notes. The diagram, not drawn to scale, shows a vehicle with a mass of 1,500 kilograms starting from rest. What does this mean? Initial velocity is equal to 0. I make a note. V initial is equal to 0. At point A, at the bottom of a rough incline, point B is 200 meters vertically above the horizontal. The total work done by force F that moves the vehicle from point A to point B in 90 seconds is 4,8 times 10 to the power of 6 joules. So, this height is 200 meters. Look at your sketch. Are you given the angle of the incline? No. And this is going to be very important in just a bit. Okay, so keep that in mind. The first question, define the term non-conservative force. So I'm going to assume now when you do your assessment, you have studied your definitions off by heart. So this is 2 out of 2. But because we're not there yet, I'm going to tell you what a non-conservative force is. A force for which the work done in moving an object between 2 points depends on the path taken. It depends on the path taken. Next question. So definitions, principles, full marks. You need to study those off by heart as it is given in the exam guidelines. But I think you've heard this before, so it's becoming boring now. Is force F a conservative force? And your answer there is no. Why? Because force F is a non-conservative force. So no, it is definitely not a conservative force. And now we get to the calculations. Calculate the average power generated by force F. So, my formula, P is equal to the work divided by the time. Do I have the work done by force F? Yes, it's given to me in the information. Do I have the time? Yes, it's given to me. It's 90 seconds. So now I substitute. Please pay attention how I always start with my formula. And then I substitute into my formula. That is very important. Even if you have to do a calculation with 0, you need to substitute that 0 value. Okay, show all your substitutions. These are marks. We do not want to lose them. So, what was the work? It was 9. No, I'm lying to you. It was 4,80 times 10 to the power of 6 divided by 90. What is the unit for power? Who can tell me that? What is the unit for power? It's watts, yes. And if you've done the calculation now there, you've typed it into your calculator, I hope you also get 5,33 times 10 to the power of 4 watt. Okay, so far, pretty straightforward. But the next question, they tell us that the speed of the vehicle when it reaches point B is 25 meters per second. So it's moving up the incline, and when it reaches this point, it is 25 meters per second. And they also told us that at point A, it was at rest. So in other words, my initial velocity at point A is 0 meters per second. Keep this in mind. Now they ask us, state the work energy theorem in words. Again, this is theory. It's in the exam guidelines. So when it's time for assessment, you know this off by heart. And I'm going to assume that you did your part. And you will be writing the following. You will write, the net work done on an object is equal to the change in the object's kinetic energy. Use the formula on the data sheet to help you to memorize the theorems, okay? Let it help you, because that's given to you. It's on the data sheet. It's there. So use the data sheet when you study definitions and principles. Next question. Now we get to the fun part. And it tells us very specifically, use energy principles to calculate the total work done on the vehicle by the frictional force. By the frictional force. So what are we going to do? There's two options. The first option, which is probably the one that is more straightforward, is to use the non-conservative formula. Why? Because I've got the initial velocity and the final velocity. I have the initial height and the final height. Why? Because the displacement of the vehicle is up the incline, certain displacement, but also there. So it's vertically as well. In other words, it is being displaced basically in two directions, you see. Do not ignore the vertical displacement. So yes, I can use the work done by the non-conservative forces is equal to the sum between the change in kinetic energy and the change in the potential energy. So, start with my formula. Which forces am I going to look at? Now, I like to always draw myself the free body diagram because then I can see what I'm going to work with. And also, if I do not draw the free body diagram, it becomes very easy for me to forget to use certain forces. Okay, so first things first. Up the incline, there's the applied force. I also have frictional force, you agree? I have the normal force, and I also have the gravitational force, or weight. But now I'm going to go one step further, and I am going to break up the gravitational force into its components, just for myself. Now, when I use non-conservative, can I include the work done by the gravitational force? No, because I'm working with non-conservative. So the forces I'm going to use is the work done by the frictional force and the work done by the force that pulls it up the incline. So let's substitute. I'm just going to break this up for you. So the work done by the frictional force plus the work done by F is equal to half mass V squared final minus half mass V squared initial plus mass gravitational acceleration height final plus mass gravitational acceleration height initial. Initially, it was 0 meters above the ground. So over here, I'm going to substitute 0. What am I going to substitute over there? The height, 200 meters. Looking at the velocities, you're going to substitute 0 for initial velocity because it was at rest. And then my final velocity, in other words, at point B, that is going to be 25 meters per second. So at this stage, you are busy substituting. Okay, you're substituting. And then we're going to look at what you get on your calculators. So, what am I calculating? I am calculating the work done by the frictional force. Do I have the work done by the force? Yes. Plus 4,80 times 10 to the power of 6 is equal to, and you're substituting. So this is going to be half times 1,500 kilograms times 25 squared minus 0 plus 1,500 times 9,8 times 200 plus, minus. Who noted that? Did you note it? Did you notice the mistake? We will be going down together. I'm warning you. Okay. please, if you see a mistake, especially with the directions, just bring my attention to it. Okay, we're in this together. I make a mistake, you're also going to make the mistake. Okay, who has a final answer for me? And before you give me your final answer, do you expect to get a negative answer? Who said yes? And you would be correct, because it's the work done by the frictional force. So this would be cos 180 degrees. So please, if you haven't watched the first two videos, you need to do that. Okay, it's very important. So, what do you get? The work done by the frictional force is equal to, I'm hoping you got the same answer, negative 1,3 times 10 to the power of 6 joules. Is that what you got? You need to be substituting. You need to be substituting, and you need to be on your calculators. So, negative 1,39 times 10 to the power of 6. Anybody has something they would like to add? Because I'm hearing a lot of you speak. You want to add something? Not. Okay. So yes, I expected to get a negative answer. What is the second option? Because I told you we have two options. This was option 1. The other option, option 2, is I could have used work done by the net force is equal to the change in kinetic energy. But I cannot use the component of weight. That would have been the easier option, because I can calculate the work done by the parallel component of weight or gravitational force by calculating the parallel component of gravitational force. How? By mass times gravitational acceleration, which would be weight, times sin, theta. But I don't have theta, so I can't use that option. But I can use the work done by the gravitational force. Why? Because I can calculate the gravitational force, mass times gravitational acceleration, and I can calculate the displacement. No, because I know it's 200 meters. And now, let's talk about the cos part. The gravitational acceleration or gravitational force is downwards, but the displacement is up. So it's going to be cos 180 degrees. And this is what I meant when we started, and I said, remember, the displacement for this specific vehicle is up the incline, but it's also vertically upwards at the same time. So I'm now going to use both of those directions. If I had theta, though, the angle of the incline, as you will see in the next example, we're going to work with the parallel component. Because in the next example, our data looks different. And that is the message I want to give you today. I cannot teach you, this is the recipe. Every single time you have to do a work energy calculation, this is what you're going to calculate. I can't do that. What I can do is I can give you the tools to use when you do work energy and power calculations. But you need to decide which tool in your toolbox are you going to use for a specific problem. And that is extremely important. Practice makes perfect. So the more you practice these calculations, the easier it will become. So let's have a look at option 2. So I always start with a formula. W net is equal to the change in kinetic energy. You can get started on changing kinetic energy so long as well. I have the work done by the force plus the work done by frictional force, which I would like to calculate, and then I'm also going to use the work done by the gravitational force is equal to change in kinetic energy. So I'm going to break this up for you just quickly. The work done by the gravitational force will be calculated as follows. You will say gravitational force times the displacement times cos 180 degrees. This is mass times gravitational acceleration, which is going to be, is it not, 1,500 kilograms times 9,8, that's the gravitational force. And the displacement is 200 meters, and then of course cos 180 degrees. You agree? And then you get an answer. And of course this will be a negative answer, hey? Because this is cos 180. We all agree. Okay, so let's give some values. Let's substitute our values. So I know that the work done by the force is 4,80 times 10 to the power of 6. Plus work done by frictional force, this is what I want to calculate. Plus, you can do the calculation and then substitute it, or you can do it as one long calculation as I'm doing, yeah? Times the 200 times cos 180 degrees equal to half of 1,500 times, what was the final velocity? 25 square. You all agree with me? You're scaring me if you just agree with me. Okay. Minus half 1,500. You need to question. Do not assume. Do not assume that I'm always correct. I might be testing you. Okay. So you need to think about this. Okay, now, do I have enough information to now solve the work done by the frictional force? Yes. You put it in on the calculator. This is the easiest part. The work done by the frictional force. Do we expect a negative answer? Of course we do, because it's the work done by the frictional force. It is removing energy from the system. So yes, negative. And I get the same answer that I got initially. And what was that answer? Negative 1,39 times 10 to the power of joules. Grade 12s? Is this my answer? Or do I need to change the negative to a positive? No, this is a scalar quantity. Remember, it's not a vector. This is my answer. And I expect it to be negative because it's the work done by the frictional force. Okay? You see, by knowing your theory, you are creating little mind notes. And when you do the calculation and you are calculating the work done by the frictional force, you already know, I need to get a negative answer. But now we do the calculations, we're sitting there in the exam, and we get a negative answer, and what do? You go, this cannot be correct. And what do? You waste 3 minutes redoing the calculation, and you still get a negative answer, because you were supposed to get a negative answer to begin with. Okay? So use these little mental notes about the theory to help you. Okay? So we're not shocked that we got a negative answer at all. Next question then, question 15. Now I want you to remember, we used the work done by gravitational force in this case, because we did not have theta. In other words, we did not have the angle of the incline. But in the next question, have a look at that diagram. Those of you at home, have a look at the diagram. Do you see the difference between the two questions? Yes, now all of a sudden I know the incline is at an angle of 30 degrees. A 70 kilogram box is initially at rest. Immediately you know what? Initial velocity is 0. You make a note because you are busy analyzing the question. So you're making notes on your question paper. You're writing there. V initial is 0. At the bottom of a rough plane, I'm thinking friction. At an angle of 30 degrees to the horizontal. The box is pulled up the plane by means of a light, inextensible rope. Rope, I'm thinking tension force. Are you also thinking tension force? Fantastic. Held parallel to the plane as shown in the diagram below. And then they tell us that the force applied to the rope is 700 newtons. So what do I know? I know tension force is equal to 700 newtons. What is the name given to the force in the rope? You just told me it is the tension force. 1 mark in our pocket. We can put it in there. Next question. Give a reason why the mechanical energy of the system will not be conserved as the box is pulled up the plane. Because of the presence of, one of you just said it, frictional force. Yes, because of the frictional force. So no, mechanical energy will not be conserved because of the frictional force in our system. Next question. Well, first they give us more information. Let's first have a look at the information. The box is pulled over a distance of 4 meters along the plane. This is very important. They also tell me that the kinetic frictional force between the box and the plane is 178,22 newtons. So let's first analyze the information we have. This is 30 degrees. If I have a look at the free body diagram, and now you need to check if I'm including everything. The first one I'm thinking of is gravitational force. Then I'm also thinking of the normal force. What else am I thinking? I'm thinking about the applied force, yes, the tension force, not the applied. The tension, yes, and I'm also thinking of the frictional force. And now, just to help myself, I'm going to break up gravitational force into its components. Perpendicular and parallel. Okay, to calculate parallel, I'm going to use sin 30 and the gravitational force. You remember? Okay, perfect. Now I continue to analyze the question. I have the mass, it is 70 kilograms, and I also know the initial velocity was 0. So I'm going to write it down here. Initial velocity is 0 meters per second. Mass is equal to 70 kilograms. Grade 12s, do we now have the height? Do we have the height? We do not. So in the previous example, we had the height and not the angle of the incline. In this example, we have the angle and not the height. So if I decide to use W net, in this case, I'm going to use the work done by the frictional force, the work done by the tension force, and the work done by the parallel component of weight. Where at the top, I used the work done by gravitational force. You see the difference in your application. And this is what I mean when I say you need to decide which tool it is that you're going to use in your toolbox. So in this case, the tool I'm going to use is, one of the tools will be the work done by the parallel component of weight. So I'll have to calculate that. Now again, this comes down to what you feel comfortable with. If you feel comfortable to first calculate the parallel component of weight and then substitute it into your formula, that's perfect. You can do that. You can do all your small calculations and then use them to substitute. Or you can do the substitution within one long calculation. Okay, this comes down to what you feel most comfortable with. So let's have a look. Draw a free or labeled free body diagram for the box as it moves up the plane. So I am now answering my question to get marks. Okay, so the first thing I'm going to do is I'm going to draw very light with a pencil. I'm going to draw the incline so that I can draw my free body at an angle as well. Okay, now I can see the incline. There's my free body. There it is. First one is the gravitational force. Yes. The next one is the tension force. Then I also have the normal force, and then just a technical point. Note that this force is 90 degrees to the surface, okay? Because that is where you will find the normal force, correct? So you cannot accidentally go draw normal force there. That will be wrong because your angle is too big. So we need to pay attention to these technicalities. Yes? Sorry? Which one? You are correct. Sorry, in this example, it is indeed the applied force. Yes. And then we also have the frictional force. Yes. I just quickly want to check. No, it is tension. Because it's an inextensible rope. I'm double checking you as well. Okay, let's continue. This is sufficient. Grade 12, please do not now include the components of weight because you're going to get a -1 because it's an additional force that you're showing. Okay, you've already shown gravitational force. Do not include the components now as well. Okay, next. Calculate the work done on the box by the frictional force over the 4 meters. The frictional force over the 4 meters. So, work done by the frictional force. First things first, I start by writing my formula. So I've got the frictional force. Do I have the displacement? Yes, cos theta. Grade 12. Am I going to work with cos 0 or cos 180 degrees? I'm going to work with cos 180 degrees. Why? Because the frictional force is in the opposite direction to the displacement. The displacement is up the incline. The friction is down the incline. So cos 180 degrees. Yes, and there was a light bulb moment there. That's what I live for. Thank you. Okay, now let's substitute what we know. Thank you. It tells me you're paying attention. Okay, that is wonderful. The frictional force was, what did they tell us? 178,22. What is the displacement up the incline? 4 meters. And then cos 180 degrees. Grade 12, do you expect to get a negative answer? Of course you do. Of course you do. And what do you get? Negative 712,88 joules. I hope that is what you got as well. Now, the next question, they ask us, use energy principles to calculate the speed of the box after it has moved 4 meters. What do I need to calculate? V final. That is what I need to calculate. V final. Do I have the initial velocity? Yes. The initial velocity was 0. So, again, I have 2 options. But now, you need to hold on to your seats, okay? Because it can get very tense now. Math. We are doing math now. Okay? How beautiful is that? Math and science coming together. And then everybody always wants to know, but why do you need math to do science? Here's your answer. First one I'm going to work with is non-conservative. Non-conservative is equal to the change in the kinetic energy plus the change in the potential energy. And now you're going to tell me, but ma'am, you just said we don't have the height. Yes, but grade 12s, if you look at your diagram, is that a beautiful little triangle? Will it be a 90-degree triangle? Will it? Aha, who knows where I'm going with this? Do you have? Yeah, yes, we have this. This is 4 meters. Do I have? Yes, 30 degrees. Can I calculate the height? Yes, you can calculate the height. How are we going to calculate the height? Let's do that first. And this is one of those things where I said you can decide to do the calculation separately first and then just substitute it. So yes, we can say, okay, but the height is going to be 4 times sin 30, and that is going to give us 2 meters. So yes, I can use non-conservative, yeah. So the work done by the tension force plus the work done by the frictional force is equal to kinetic energy, half mass, and the mass is 70, V final minus V initial, so V final, what I want to calculate, don't forget the square, minus 0 squared, plus, what is the mass? 70. What is gravitational acceleration? MGH, 9,8. Can you see, as we are continuing now, I'm starting to take shortcuts because I know the formula now. See? And this comes with practice. Then you can start to skip a step or two because your mark will be there. Nothing keeps you, though, from writing the next formula as well or breaking it up. You can do that. It comes down to what you feel most comfortable with. And then, my initial height, how many meters above the ground? It was 0 meters above the ground. And then 2 meters. So 2 minus 0. Yes. And now I can calculate the work done by the tension force because I know the force is 700 newtons, as well as the work done by the frictional force because I have that as well. Do you all agree? Fantastic. Remember what I told you? You need to double check me, eh? Tell me. The tension force, was it in the same direction or in the opposite direction to the displacement? Same. So what am I going to use? Cos? Yes, cos 0. Honestly, grade 12s, you no longer need me. Huh? What was this? 178,22. Is that correct? The displacement was 4, but I'm using cos 180. Thank you. And now I do my math, and what do you get? I'm just going to be lazy and do this, also because of time. You do the math, and you solve V final. Again, nothing keeps you from showing those steps here as well. What do you get there on the calculator? What do you get? I'm wondering. Your 4 comma, you're correct, 4 comma, 5, 2, is that what you got? V final is 4,52 meters per second. You agree? Okay, so yes, if you really wanted to, you could use non-conservative, but then you will have to remember that you do not have the height, so we should probably then calculate it when we use the height. Did we need the height here though? Grade 12, are we all still awake and on the same page? Okay. The next option, because we had potential energy there, so obviously we used the heights as well. But now, let's say you thought to yourself, listen, I don't have the height, and I don't know how to calculate height because we are writing physical sciences, so we're slightly stressed. You don't need it. We can just go with W net. This would have been my first option though, because I'm slightly lazy. So don't have to do that many calculations here. But now, I need to consider what? I cannot ignore the work done by the gravitational force now. So in other words, I'm going to have the work done by the tension force plus the work done by the frictional force plus the work done by the component, the parallel component of weight, which is equal to the change in kinetic energy. You agree? Okay, so I am given the tension force, I can just substitute it. I'm given the frictional force, I can just substitute it. Do I have the parallel component? Not yet, but I need to calculate it. And can I calculate it? Yes, I can. So you can decide that you would like to do this calculation separately, and then you're just going to substitute it. So it's going to be mass times gravitational acceleration by times sin 30. Agree? Okay, so what was the mass? 70 times 9,8 times sin 30, and we get 343 newtons. You agree? Okay, so now I can just substitute that into my calculation, or I could have included this whole part in one big calculation. This really comes down to what you feel most comfortable with. So this is going to be the tension force, which is 700. What is the displacement? 4. Tell me the tension force is in the same direction as the displacement, so it's going to be cos 0 plus. Have I already calculated this? The work done by the frictional force. Yes, I calculated it in 15.4. So grade 12s, if you made a calculation error, have you ever heard of positive marking? I'm certain you have, because you always ask me when you come back after an assessment, but what about positive marking? If you substituted something you've calculated in a previous question, and that was an incorrect value, but you substituted it correctly here, we usually apply positive marking. Okay, so no need for you to stress if you've made a calculation error. Okay, just substitute what you calculated. Okay, so the work done by the friction, was there a question? Is there not? Okay, so the work done by the frictional force was negative 712. But just to show you again, I am going to include it again, whole calculation, which was 178,22 multiplied by 4 multiplied by cos 180 degrees plus 343 times 4 times, is it in the same direction or in the opposite direction? Opposite to the displacement, so here I'm also going to use cos 180, you agree? Is equal to the change in kinetic energy. Now, you can decide to first simplify this, and then over here I'm going to continue with the calculation. Half times 7 times, what am I calculating? The speed of the box after it moved up the 4 meters, is that correct? Okay, so help me with the substitution, yeah? What am I going to substitute? What am I going to substitute? I'm calculating V final. So I can substitute V initial. which was 0. Remember. So I want to calculate V final, don't forget about the square, minus half 70 times 0 square. I've shown my substitution. And now I can choose if I'd like to break it up some more for myself to make it easier, or just go straight to V final. And if you do that calculation, take a guess. What do you think is our answer going to be? 4,52 meters per second. Yes. Well done. And then we get to the final question. So you see now that we do not only have one option. We usually have at least two. You as an individual will decide what you feel most comfortable with. But if you do decide on using non-conservative, please, you have to remember, you cannot include the work done by the? Yes, not the work by the gravitational force. And that's the trick, okay? And yes, you can use your Pythagoras and you can use trigonometry to calculate components which was not given to you. Making sense? The only thing you really need to remember here is that you need to show all your calculations, okay? You can't do a quick calculation there. Do you have a question? Not. You cannot use a value that you have not shown the calculations and you were also not given the value in one of your calculations. You always need to show us where you got the value from. Okay, so especially if you calculate it, don't do a quick calculation here on your calculator and use it without showing how you got to it. So always remember you need to show all of your calculations. Now, question 15.6. When the box is 4 meters up the incline, the rope accidentally breaks, causing the box to slide back down the bottom of the inclined plane. What will the total work done by friction when the box moves, we want to know the total work done by friction when the box moves up and then down to the bottom of the inclined plane. What will it be? What will it be? It goes up and down. It goes up and down the incline. So in other words, it will be double the 712.88 joules. So times 2. Okay. Any questions, grade 12s? This brings us to the end of work, energy, and power. So there's an additional question that I would like for you to go and do on your own at home. And I would like for you to practice doing both methods, both approaches. So I'm going to give you a quick clue. I'm just going to give you a tip. At question 16.5, that's the one I'm referring to, where you've got two options. I will post the answers to this question next week. Okay, so you've got a whole week in which you can quickly go have a look at that question. And at question 16.5, see if you can do both applications. The one using the work done by the non-conservative forces as well as the net work done is equal to the change in kinetic energy, which is also known as the work energy theorem. Okay. Thank you. That's the end of my story for today. Thank you.